Here is what we're going to do for the rest of the semester. We are going to state and prove Green's theorem. You may, I hope you do remember Green's theorem from Calculus 3. But in case you've forgotten, let's recall how this works. Let's suppose we've got a two-dimensional region, which I'm going to call omega. And Green's theorem is explicitly a two-dimensional result. There are higher dimensional analogs, but we are not going to get there this semester. And then for a sufficiently nice region, at least, you can talk about a tangent vector to the boundary of omega. And then if you've got two sufficiently nice functions p and q that are defined on omega up to the boundary, then you can write down this formula. The two-dimensional integral over omega of the function partial q partial x. This is a we're going to be living in two dimensions for a while, so I'm going to go back to using xy coordinates instead of having the coordinates be x1, x2, they'll just be xy. So partial q, partial x, partial derivative of q with respect to the horizontal variable, minus the partial derivative of p with respect to the vertical variable. That is equal to the integral over the boundary of omega of the vector PQ dot product with the tangent, and then integrated with respect to arc length. So we are going to prove that this formula is true for at least sufficiently well-behaved regions omega in R2 and sufficiently well-behaved functions P and Q. But to prove this theorem, we're going to need to state it precisely. So to even state this theorem, let alone proving it, a lot of the work we're going to do is just defining what all these things mean. So what do we have to define? We have to define two things. We have to know what this double integral over omega is, and we have to know what this integral over the boundary is. The boundary, at least for a nice region, is a curve. It's a one-dimensional thing. So integration over a curve. Your book scatters analysis of curves throughout. So this is section 6.1, 7.1, and 8.1. We will gather them all together. That's reasonably straightforward, but I would like to start by talking a little bit about what do we mean by integration over a two-dimensional region. Now, I want to spend a minute on how your book is organized and how that's different from how we're going to finish up this course. So chapter 7 in your book that covers Riemann integration in 2 dimensions. You remember Riemann integration is chapter 3 in your book and is the last topic we covered at the end of Math 4513. Now, I don't really want to do chapter 7 as written, and there are 2 reasons for that. So the first is that 2-dimensional or 3 or 4 higher dimensional Riemann integration is a lot more complicated than 1-dimensional Riemann integration. There are a lot of very annoying technicalities, a lot of annoying little lemmas that you have to prove. So it's just a big pain. Now, you do have to work out a satisfactory theory of multidimensional integration at some point because people do care about that. It's an important branch of mathematics, but there is something called Lebesgue integration, which has the following properties. It is more powerful than Riemann integration. There are lots of functions that are Lebesgue integrable. The Lebesgue integral of that function is well defined, but the Riemann integral is not. And for that reason, pretty much everybody who does real analysis has to learn the Lebesgue integral anyway. So if we skipped 2-dimensional integration, now those of you who go on in mathematics will see 2-dimensional Lebesgue integration, which is better than 2-dimensional Riemann integration anyway at some point. So I don't feel like you're losing anything by not doing chapter 7, not doing 2-dimensional Riemann integration. And 2-dimensional Riemann integration is enough of a pain that I just don't want to do it if we can avoid it. And Lebesgue integration generalizes easily to higher dimensions. Riemann integration is simple in 1 dimension, complicated in 2 or more dimensions. Lebesgue integration is already pretty complicated in 1 dimension, but it gets only a little bit more complicated in 2 or more dimensions. So we're going to procrastinate. We're going to let you put off really doing 2-dimensional integration until graduate school. So I don't want to do a 2-dimensional Riemann integration, and I don't want to do chapter 7 as it's written. So unfortunately, the chapter 7 lectures I'm about to give you reading along in the book won't help because we're going to be doing something very different. I'm sorry about that, but I think this is what we have to do what I want to do with this. And we don't want to do Riemann integration in its full glory. 2-dimensional Riemann integration in its full glory. So what we're going to do instead is we're going to do what I'm going to call Fubini integration. So this is how you integrate over a two-dimensional rectangle, and we'll talk about two-dimensional shapes that aren't rectangles later. So we'll pick 4 real numbers such that A, B, and CD are both non-empty closed bounded intervals. And let's let capital F be a function whose domain is this rectangle, this two-dimensional rectangle, whose domain is a subset of R2. It's a function from the rectangle to the real numbers. And then we say that F is, and I'm going to put this in scare quotes, Fubini integrable. If the following long and annoying list of conditions is true. The first thing we need is that for each x in AB, we need the integral of f of, we're freezing the first variable, we're fixing it at x. We need that integral to exist. And that's in the sense of chapter 3 of one-dimensional Riemann integration. And I'll point out that since we're going for Green's theorem, we're only doing two-dimensional integration, not p-dimensional integration. So I'm going to go back to referring to the coordinates as the x-coordinate and the y-coordinate, not the x1 coordinate and the x2 coordinate. That's a little different from how we've been doing things back in chapter 6, but is consistent, I hope, with what you're used to. All right, so we've specified that for each x in AB, this integral here, this integral exists. This is some number. So we can think of this integral as being a function of x. So what we need is we need the iterated integral, the integral from a to b of the function of x that you get by taking the integral of f of x y dy. You fix the first variable at x and you integrate it in y. That gives you a function of x. If that is also integrable, in the sense of definition 3.1.3. So that's the second thing we need. The third and fourth things we need are the same thing with x and y interchanged. So we need our function f to be integrable in x if for any y value you pick, any y value that you freeze, and we also need the iterated integral done in the other order. We also need that to exist in the sense, as usual, of definition 3.1.3. And so to be Fubini integrable, you need to be able to integrate first in x, then in y. You need to be able to integrate first in y and then in x. And here's the key thing. We need the two iterated integrals to be equal to each other. And why am I putting Fubini integrable in scare quotes? I'm doing that because this is not standard notation. Real mathematicians care about Lebesgue integrable functions, or occasionally Riemann integrable functions if you're in one dimension, and so Riemann integration is actually easier. And then the reason why I'm naming this form of integrability after Fubini is that Fubini's theorem says that if f is Riemann integrable, which I haven't defined for you and I'm not going to, but people did do a lot of math about it. Riemann integrable on the rectangle. Then you can do iterated integrals in either order. So our Fubini integrability condition is true. So Fubini's theorem says that all Riemann integrable functions, whatever that means, are Fubini integrable in the sense I've defined above. So this isn't standard notation, but it's we've written down a perfectly good, rigorous definition, so we're allowed to use it, even though we're mathematicians and engineers. We aren't waving our hands at anything. It's a perfectly good, pure math definition, and everything we're going to do for integrable functions, for Fubini integrable functions, will work for Riemann integrable functions. If you ever do in your life, look up the definition of Riemann integrable functions. And so this is going to be good enough for what we need. One more quick piece of notation. Remember how we write Riemann integrable on AB? We don't write Riemann integrable on AB. We write it cursive R and then AB. I'm going to do the same thing for Fubini integrable functions. So cursive f of AB cross CD is the set of all functions f defined on from AB cross CD mapping into R, all real valued functions on that two-dimensional rectangle such that f is what we're calling Fubini integrable. So let's prove that some functions are indeed Fubini integrable. And our final statement of Green's theorem, by the way, won't use the term Fubini integrable at all. We'll just prove it for continuous functions. And so this strange new terminology that I've introduced won't show up when we get to our goal. So let's take 4 real numbers as usual. And if I write A is less than B and C is less than D, I mean that A, B, C, and D are all real numbers, because real numbers are the only things where you can say they're less than something else. Let's let G be a function that is Riemann integrable in the one-dimensional sense on the one-dimensional closed-bounded interval AB, and let's let H be Riemann integrable on the other interval. And then we're going to define a new function, their product. Let's let f of xy be g of x times h of y. G and H are Riemann integrable functions, so they're real valued functions. There's functions from A, B, or C, D, respectively, into the real numbers. So their product is a real number. So our product F is now a function from our rectangle AB cross CD to the real numbers. So it could conceivably be Fubini integrable, and the conclusion of this proposition is that f is indeed Fubini integrable on this rectangle. So now let's write out the proof of this. So first notice that if x is a point in our interval, then g of x, G is an integrable function, so it maps to the real numbers. So G of x is just a real number. So the function G of x times h, that is a real number times h. H is Riemann integrable. So this is Riemann integrable on the interval CD. And this is true by proposition 3.1.11 from last semester. And furthermore, the integral, the one-dimensional integral of f in y, that is the integral of g of x h of y dy. G of x is just a real number, so we can pull it out by proposition 3.1.11. And I'll just write the integral of h and not bother writing the y's. Now we do the same thing with this real number. H is integrable, so its integral is a real number. So again, by the same proposition, 3.1.11, this real number times g is a Riemann integrable function on AB. G is an integrable function on AB, so we multiply it by a real number. We're still Riemann integrable. And let's write down our integrated integral. That's the integral from a to b of the thing we found above, g of x times the integral from c to d of h dx. And then we can move the integral of h out because it's just a real number. Then we can make a similar argument, and I'm not going to drag you through it to see that the iterated integral in the other order, all the pieces that need to work. And in this case, you end up pulling out the integral of g times the integral of h, but multiplication in the real numbers is commutative. So this is indeed equal to the double integral, the iterated integral in the other direction. And that is all there is to that. Here is another proposition. It is pretty similar to proposition 3.1.11. It says that the set of Fubini integrable functions on any rectangle that is a vector space. That means that if f and g are Fubini integrable, and alpha and beta are two real numbers, then the linear combination alpha f plus beta g, that is also Fubini integrable. And you prove it by invoking proposition 3.1.11, like we did before. And furthermore, you get the double integrals. You can break them up exactly how you think you should be able to break them up. The only difficulty, of course, is writing these things down. You get alpha, then the integral of f of xy dy. Then you add to that beta, and then the integral. Or, of course, you can do these integrals in the other order because they're Fubini integrable. And there is a particular special case. We can put the two propositions on this page together. If I've got a bunch of Riemann integrable functions, one-dimensional Riemann integrable functions, got a whole bunch of them. The first proposition on this page says that their products are integrable, and the second proposition says you can add them together. So this sum So if f is given by this sum, then the sum f is Fubini integrable. Now, your homework for this section is going to be, you are going to prove that all continuous functions, if you've got a function that's continuous on a closed bounded rectangle, then it is Fubini integrable. But I think to do that, it will help if you have proposition 7.3.1. As it happens, this is actually proposition 7.3.1 in the book. I think this will help you a lot with your homework, which is going to be proving that continuous functions are Fubini integrable. So how does this proposition work? This says if you've got a function defined on a rectangle, and I think I'm going to take it as a given from now on that any rectangle, that if I write a rectangle like this, I mean that A is less than B, C is less than B. So we've got a function on this rectangle that is continuous. And then we're going to show that f is arbitrarily close to a function that's Fubini integrable. So we're going to pick a positive number epsilon. And the conclusion is that there exists a natural number n and functions gk defined on AB, hk defined on CD, for each, there are n of these functions, or rather n pairs, such that each gk hk is indeed continuous, and we've got this difference. Your function f is arbitrarily close to the sum of the gk's times the hk's. Actually, let's have one more function. Let's start at g0 instead of g1. Now, we are not going to use the proof in the book. This is because the proof in the book uses section 5.7, and we didn't cover section 5.7. It uses some heavy machinery, the Stone-Weierstrass theorem, but fortunately, this isn't terribly hard to prove. I hope it's obvious to everybody that a rectangle, if A, B, and C, D are finite numbers, this is clearly bounded, and it's not at all hard to prove, but you can use the techniques from early in chapter 5 to show that this is closed and bounded. And it's a subset of R2. So by the Heine-Borel theorem, This is compact. And we love compact sets. So one of the things we love about them is that a continuous function on a compact set, it's better than continuous. It's uniformly continuous. All right, we've got a uniformly continuous function, and we've got an epsilon. So by definition, 5.4.11, there is a positive delta such that if I've got 2 points in my rectangle, now I've got to call them something, so I'll let the coordinates of the other one be ZW, if they're both in our rectangle. And the distance between them, which we remember in Euclidean space is given by this norm. If that distance is less than delta, then f is a real valued function, so I can just take an absolute value, not a norm. And that's less than our epsilon. By the Archimedean property, there is a natural number n such that b minus a over n, I want that to be less than delta. And now let's define these approximating functions. I'm going to let xk be a plus b minus a over n times k. So x naught is a, xn is b, xk plus 1 is xk, and then you add this number, b minus a over n, which is positive but less than delta. And we're going to let hk of y be capital F of xk comma y. So for hk, you just freeze an x value and you let your y run along. And because f is continuous, hk is continuous. All right, and now the GKs are going to be a little bit more complicated to define. So the GKs are going to look like this. So here are some nice coordinate axes for us. Here is our point A. Over here is our point B. Then somewhere in the middle, we've got xk, xk plus 1, and xk minus 1. Or possibly xk is the end point. It's not too hard to deal with that case. And then our gk, it's going to be 1 at xk. It's going to be a straight line segment going down to 0 at xk plus 1 and xk minus 1, and then it's going to be 0 all the way down to a and up to b. Writing down the definition of a gk as a piecewise defined algebraic function. It's not terribly hard, so I'll do it, although I think the picture gives you most of what you need. Then it is a fraction between xk minus 1 and xk. This slightly different fraction, xk plus 1 minus x over xk plus 1 minus xk. And you can check that this is indeed a well-defined function because on the numbers that are showing up in more than one case, xk minus 1, xk and xk plus 1, you get the same answer, whichever case you're in. And then we can conclude that gk is continuous on, in fact, on the entire real lines. And so of course, in particular, it's continuous on this interval. All right, so now we know what our HKs and GKs are, and we've seen that they're both continuous. Now we just need to show that F is close to the sum of these GKs and HKs. So let's pick some point XY that's in our rectangle. And then because X is between A and B, then it's between some pair of the XKs. So let's let J be the index of the pair it is. It's between. So there is a J a natural number J between 0 and n such that xj is less than or equal to x. X is allowed to be b, so it's less than or equal to xj plus 1. And now let's think about what the GKs are doing. First off, let's notice that if k is less than j, then because k and j are both integers, k plus 1 is less than or equal to j. And so because the xk's are an increasing sequence, we have that xk plus 1 is less than or equal to xj is less than or equal to x. So gk of x, look at your definition of gk, it's 0. And pretty much the same argument. If k is bigger than j plus 1, then gk of x is equal to 0. And so when we take our sum, the only GKs that show up are GJ and GJ plus 1. And what do those add up to? GJ of x plus GJ plus 1 of x. Well, GJ of x, we just write down the definition, xj plus 1 minus x over xj plus 1 minus xj. And then if you think through what gj plus 1 is, you get x minus xj over xj plus 1 minus xj. And when you subtract them, the x's cancel out and you're left with just a 1. And also note that GJ is always between 0 and 1. And so GJ plus 1 is also between 0 and 1. So let's write down the thing that we're trying to show is less than epsilon. So f of xy minus this sum that's f of xy, and then we only get two terms left. And now we're going to use the fact that GJ and GJ plus 1 add up to each other to write f of xy that as GJF plus GJ plus 1f. And now I'm going to write down what HJ is. Remember, that's f of xjy. Now we're going to use the triangle inequality and the fact that GJ plus 1 is not negative. But x minus xj is less than b minus a over n is less than delta. Same for xj plus 1. So the distance between these points, xy to xjy, xy to xj plus 1y is less than epsilon, is less than delta. So we've got that f of xy minus our sum that's less than gj of x times epsilon plus gj plus 1 of x times epsilon, which is just epsilon. And that was all we were trying to prove.